Hello, I'm Sylvaine Tanser from KTH Stockholm, previously from the Department of Computer and System Sciences at Stockholm University with Barry Brown, and with whom I conducted this study, and Oskar Lindvall from the Applied Information Technology of the University of Gothenburg. This paper is called On Pause: How Online Instructional Videos Are Used to Achieve Practical Tasks. So, online instructional videos first. Most commonly YouTubes. We're all familiar with them. They are watched by the millions every day for entertainment, such as cooking TV programs also, or to achieve an unfamiliar task, which is their primary goal. You don't know how to do something, you go to an instructional video. The videos themselves are designed as instructionals. They are designed for users to achieve the task. For example, they pass the task in visible small steps through, for example, the voiceover or some inserted text in the video. And they give privileged access to the visible details of objects and live actions, for example, with zooming in or slow motion with actions. But while the design and the content of the videos themselves is, of course, very interesting from a technology design point of view, we wondered how those videos are actually used and how, for example, the users rely on the features I've just described about the videos themselves. So we decided to conduct an ethnomethodological study, that is, looking at members' practices, unpacking the methods through which actors conduct such activities. And the point is to uncover the unremarkable, looking at what is seen but unnoticed usually. That is, what people, when they're doing it, will not even notice, not even mention, dare to formulate. But these seen but unnoticed methods and practices are extremely relevant and interesting, notably for technology design. So what are the issues in following video instructions for users and also for HDI? Well, first, regarding following instructions, as I said, we know that instructions provide a frame of reference for actions, but they are completely decontextualized rendering of practices, by a sense indexical and necessarily incomplete. That is, to follow instruction, the user has to provide a certain work to transform these decontextualized renderings into actual, real, lived courses of actions within their local circumstances and considering many contingencies that are not included in the instructions. More specifically, for example, the objects that users have at hand when they try to follow video instructions are not necessarily the same as those in the video. So how do they address what Livingstone calls this correspondence problem? Another set of questions is around the coordination of temporalities. While tasks progress sequentially, and videos of course follow this sequential progression, videos also have their own temporality. They progress at their own pace, and on the other hand, users can progress at their own pace as they try to reproduce the actions that are being shown and told. So how do users coordinate those temporalities? And one way that they can do that, but still needs investigation, is how users interact with the video as a medium through the interface, the various interfaces such as the player, the mouse, the cursor, the buttons, etc., to coordinate the temporality, to address the correspondence problem. And based on this, we can draw design recommendations. So for this study, we video recorded 10 pairs of participants achieving a variety of practical tasks using online video recordings. Here you have an example of two users replacing the brakes on a bicycle, and you can see the 3 camera angles that we had in order to have a good access to their actions, and the screen recording on the bottom right image. To analyze the recordings, we use the methods of conversation analysis, which is the expertise of our 3 authors. And we noticed that pausing was very often used. It's a very simple function, and at the same time it used to achieve a broad variety of actions. We got interested in pausing, and we analyzed a collection of pausing systematically. And this led us to identify 4 types of pausing with very typical features and recognizable features. The first one is when an instruction is in progress, participants can pause to establish the correspondence between what they see in the video and what they have in their own world. That's when this connection between the two begins to emerge. They pause, they re-establish correspondence, and then they resume the video. Now, the second and the third types of pausing correspond to 2 different ways of organizing the activity. Users can either alternate between watching the video and achieving the task, or they can achieve the task while the video is playing. In the first case, they would recognize the upcoming end of a step in the video and pause right at the end in order to turn to action and to reproduce that exact step. In the second case, when they achieve the task while the video is playing, they would pause before falling behind. When the instruction for the next step is starting in the video, they would pause to complete the previous task and then resume when they have caught up with the video. Now, the fourth type of playing is slightly different, of pausing is slightly different, is when they are replaying the video after they have encountered the problem while trying to reproduce, to follow the instruction. They would pause in the middle, anywhere within an ongoing instruction, when they have just seen the solution to their problem, and they would pause to fix that problem in their own world. I will show now an example of the second type of pausing, when users alternate between watching the video and achieving the task. You will see how here they pause exactly at the end of an instruction of a subtext, of a step in the video, just before turning to action. On the right hand side you have the screen recording, and on the left you can see the two users watching the video.
In order to do that, we need to release the quick release mechanism on the cable, which is done by opening up the little rubber boot and pulling the calipers together and unhook this L-shaped tube called the noodle. Okay, let's do that.
You want to start?
You can see clearly how they anticipate the end of the step by bending towards the space button, and they pause exactly as the instructor's falling intonation shows that this step is over, and that's how they rely on the features of the videos themselves, the design of the video. But to conclude and discuss and conclude this, we were able to draw from these findings some design recommendations for videos themselves and for video tools to better support instructions following. For example, we suggested that video producers could be provided with a possibility to insert frame-in-frame images that would show a new object or a new tool before it is introduced and would stay for a while on the image, so that to enable users to identify and locate these particular objects or tools in their world. Or we could imagine a more informative timeline where permanently the transitions between the different steps of the task would be displayed to support the second and third types of pausing that would assist user in pausing at the right moment. Our point here was to show that this very basic user interface function, the pausing, can have considerable complexity when it's incorporated into and part and parcel of complex activities when it is looked at in use, of course. And following video instructions consists in actually weaving together the video and the physical task as one and the same course of actions, because it's about following instructions. And this paired nature of screen-located activity and physical activity is actually a very common feature of contemporary apps and technology use more broadly. So to conclude, we contend that this approach and our findings have applications far beyond the use of instructional videos. Thank you very much. We wait for your comments and questions.
Spatial recordings allow viewers to move within them and freely choose their viewpoint. For example, NBA 360, Minecraft, and Fortnite recordings allow the viewer to move through the scene, choose their perspective, and skip through the recording. This gives viewers more control over their experience, but also puts a burden on them to use this freedom effectively. Let's take as an example a spatial virtual reality recording of a kitchen scene to illustrate this problem. The viewer of such a recording can look anywhere and explore. For example, the viewer might wonder, who put the can on the counter? Or where did the can end up? To find the answer, the viewer might scrub a timeline or fast forward through the recording. However, this makes it easy to miss events, as well as challenging to follow moving objects. In the case of large fast-forward speeds, it can even cause nausea. Is there a better way of navigating spatial recordings? We propose direct manipulation of objects within the scene to navigate through time. By selecting an object, the viewer can step through the moments where the object changed. For example, by selecting a dirty pot, the viewer can see who put it in the sink or who cooked with it. The viewer can also reveal the trajectories of objects that change location and directly manipulate them to move through time. Our techniques are based on two key ideas. The first key idea is that the viewers are interested in moments of change. For example, a viewer of a spatially recorded basketball game might be interested in the moment that the ball changes trajectory to see if a player touched it before it went out of bounds. The second key idea is that we make the direct manipulation of changing objects central to navigating through time. Instead of having to use a timeline, the user can directly interact with the objects within the scene to navigate. We design the Who Put That There temporal navigation system by building upon these two ideas. To enable such object-based navigation, we first need to track each object's change of location, appearance, configuration, and its interactions with other objects of avatars. Viewers can then select the objects and preview these changes in two ways: by stepping through notable changes, or by showing the object's trajectory, which indicates the change in location. These previewed changes can then be used for navigating through time. Stepping through object changes works by hovering over an object and pressing left or right on the thumbstick to preview what happened to the object before or after their current time in the spatial recording. The preview is then rendered in a transparent sphere, showing the selected moment as a looping animation. We also show a contextual indicator that directs the user to the previewed change and indicates the relative time to it. Scrubbing objects' trajectories works by selecting an object to toggle its trajectory and then scrubbing along it or jumping at any point at the trajectory. By doing this, the viewer moves to the time in the spatial recording when the object was at the selected position. The viewers can also reveal the trajectories of objects in another way. By enabling the trajectory sphere, the viewer can scan the environment to see all the trajectories that passed through it. This can help find objects that have already left the scene or to find objects that were used at the specific location. In addition to the object-based navigation techniques, our temporal navigation system also includes a timeline and a conventional media controls, such as fast forward, rewind, play, and pause. Navigating through time by direct manipulation of objects within the scene has a number of benefits. It allows for easy mapping of intentions to actions. If a user is interested in who put that there, they can select that and quickly find the answer. It previews the changes in the scene. So instead of previewing the changes in a separate picture-in-picture view, the previews are at its actual location and at their actual scale. It integrates coarse and fine-grained navigation. Spatiotemporal trajectories naturally have higher resolution when more change is happening and lower when the objects are static. It supports sense-making by quick query of objects, scanning of the scene, and discovering of causal sequences. To learn how users experience object-based navigation, we evaluated the Who Put That There system in a Think Aloud study with 11 participants. In particular, we were interested in whether the system was easy to use, understandable, and useful. Participants were given a 22-minute-long spatial recording and a set of sense-making questions. Questions such as, what happened to the red mug? Or why was a hamburger thrown out of the window? To answer the questions, participants had to navigate to the relevant parts of the recordings, either by stepping through objects' changes by using the object's trajectories, or by using the timeline. In all cases, the participants could also use conventional media controls such as play, pause, fast forward, and rewind. 3 topics emerged from the thematic analysis of the Think Aloud study and the end interviews. We named them being there, making sense, and having fun. The participants expressed that object-based navigation techniques felt more like being there, while using a timeline was more like watching a movie. One participant mentioned that using the object-based techniques felt like playing a game, even though the possible manipulations of objects were constrained to the recorded ones. When using objects' trajectories to complete the sense-making tasks, participants also mentioned a greater understanding of what had happened and the context around it. One participant compared using the timeline to reading the ending of a book to find out what happened, and using objects' trajectories to reading the full book and seeing how it happened. Most of the participants also mentioned that using object-based navigation was fun, interesting, and cool. Participants were quick to learn and use the full functionality of the system, despite most of them having little or no prior VR experience. Object-based techniques did require more explanation than timeline and media controls, as participants were familiar with the latter two from traditional video recordings. However, all participants were able to use the object-based techniques well enough to answer all the sense-making questions. We believe that using direct manipulation techniques for temporal navigation shows promise and can be especially useful for spatial recordings. However, there are limitations to the presented concept, the who put at their system that exemplifies it, and the evaluation of the system. First, direct manipulation techniques might not be suitable in all scenarios. Our concept requires active engagement with a scene, which can become exhausting or cumbersome in cases of complex queries. Second, the who put that their temporal navigation system is only one instance of the presented concept. It does not track, preview, and allow navigation by all possible changes that could happen to objects and avatars. It also previews these changes in 2 specific ways. Tracking more changes or previewing them in a different way might work better. Third, our Think Aloud evaluation has limited generalizability as we only tested one scenario and recording duration. For a more comprehensive evaluation of the usability of specific techniques, a comparison of them in the different scenarios would be needed. Despite these limitations, we believe that using direct manipulation with spatial recordings to control time has many benefits and should be explored further. We envision similar interactions as presented to be possible in augmented reality in the near future. Navigating through training materials that come in the form of spatial recordings could be especially useful. Apart from AR use cases, complementing spatial game replay systems with some of the presented direct manipulation techniques could also prove useful.
Thank you for listening.
Yay, thank you, Clement. Anyone has a question for Clement, then please type your name in the chat. I also want to, I also want to say, as I wrote also in the chat, that Shaman's presentation will come after this, so we will take a bit of a break, but that's better than try to reschedule it for another day. So please, if you have questions. Sylvain, yeah, please start.
Yes, thank you very much for this presentation. Now I see what you were talking about with augmented reality and the link with the former presentation. That was very interesting. It made me think of, now it was very dense, so forgive me if I missed something that you said, but you were talking about mainly video games, I think, right?
Yeah, we didn't frame it only around the video games, but VR spatial recordings. So whatever that application is, be it drawing, be it something like TiltBrush, it can be many things. But we focus specifically on virtual reality.
Yeah, okay. I don't know if it's really, if I'm heading to a question, but it made me think of typically this would be very convenient for cooking activities, and you showed some activity in the in the kitchen with cooking things and objects. And obviously, this was something that I've been investigating. Besides the how we could assist people in doing some cooking activities, and we noticed that very often where objects are located, when you use them several times during cooking session, is really a problem for people. So I guess in terms of training or some sort of support, this would be a very convenient tool. I don't know if you thought about this, but so it was just a comment, I guess.
I think it would be super interesting. Yeah, also maybe looking into or doing a study how it might facilitate memory, because if you look at an object, it might be easier to then remember what you did already or jump to the stage of some specific stage of cooking, for example. So definitely a super interesting idea.
And Ahmed, you had a question? Yes.
Thanks. Thank you for the presentation. It is really interesting to see all these trajectories going from one object and involves the person. Do you think that this might be also used with AI kind of approach, or with machine learning? Maybe who will put that there kind of approach, you know, like instead of the past, exploring the future and try to sensitize yourself to possible places of the objects in the future, maybe. Do you think this kind of interaction would enable that, or?
Just to be sure that I understood it, if AI could be used to improve the visualizations of trajectories, for example, or
on mute now, yes. Both that, but also in terms of you involving AI to calculate potential actions in the future, so that we can see where a certain cup would take place in a new recipe. Talking about Sylvain's example, for example.
Yeah, that would be very, very interesting, I think, because this system is now focused only on what's already happened. So on everything that happened until now. But based on this, you could make predictions about the future, and then you could, show the trajectory of where something will go, and that might be used as a reminder. Oh, hey, you should go there because this is what you usually do every day. You have to feed your cat or something. Or it could maybe be interesting to also look into how seeing those predictions then changes your behavior. Maybe once you see that you're going to take chips like every 3 minutes, maybe you would then not do that. So I think it would be very fun to make a system that involves AI and makes predictions of your movement or actions.
Thank you very much, Clement. We will take the last couple of minutes of your questions to give some time for Germain to start his presentation here instead. I hope that is okay, so that we still get a little bit of break before the next session starts. But thank you very much, Clement.
Thank you.
And imagine again the virtual applause. So Germain, sorry for all this. I hope you're still okay.
This happened. Okay, so let's start. Hello, my name is Germain, and I will be presenting Pronto. I hope you are seeing the presentation. So let's start by saying that prototyping is at the core of interaction design. From static sketches in a napkin to quickly visualize the user flow, to physical prototyping with clay, for example, to explore the form of a design. However, some designers rely on video to prototype dynamic system responses, and we saw it recently. They combine paper prototyping with the wizard of technique to let them play the role of the computer. But how a technique like video prototyping can be used specifically for augmented reality? Well, if we have time and money, we can use video editing software to create an illustration of the AR experience, like Google did here with Project Glass. If not, in 2018, I introduced a new video prototyping tool that is called Montage that let designers quickly sketch and animate on top of video. However, this is only in 2D, faking the AR experience without any 3D information. So what are the current tools that give AR designers access to 3D positioning in space? First, we have the development tools. They require programming and include game engines such as Unity or Unreal. And we have also SDKs like ARKit for iOS and ARCore for Android. But this slows down the prototyping speed, particularly in early stage design, and also exclude non-programmers. There are few commercial prototyping tools that don't require programming. However, they focus heavily in face tracking AR, or they provide limited sets of pre-created interaction triggers. To sum up, current tools generally focus on pre-made assets instead of creation, static or fixed animations rather than dynamic scenarios, high instead of low visual precision, and default interactions rather than exploratory user inputs. With this in mind, what would be the design goals for an early stage AR prototyping tool that is simple to use, but also powerful enough to create open-ended designs? To inform the design of this tool, we conducted 3 formative interviews with expert AR designers to identify current issues in early stage AR design. 4 problems stood out. First, all participants mentioned a vast ecosystem of tools to create 3D assets. Other problems are consequences of freedom that the user has while using the system. One of the biggest challenges when designing for AR is the designer's inability to control the camera. Participants also said that the most tedious task is positioning 3D assets. P2 mentioned that positioning is problematic with depth and occlusion. Also, designers consider animation a pain point that avoided laborious manual animation like keyframing during early stage prototyping. To tackle these problems, we propose the following goals. One extra implicit goal is providing a lower barrier of entry to any stakeholder. To achieve this, we made the following decisions. We will use a single mobile device to provide a low barrier of entry. We will use sketching to create low fidelity assets. We will use video to capture the always changing position of the user, and direct manipulation, again, through demonstration to position assets and to animate them. With this decision in mind, we built Pronto. Let's introduce Pronto with a scenario. Imagine a designer that is prototyping an augmented reality smart home. He wants to place AR objects on top of a coffee table, turn on the TV with a flick of a finger, and send likes with mid-air gestures. The first step is acting and capturing. This happens in Pronto's recorder view. After 3 seconds countdown, the designer starts moving in the environment as if the AR system is already in place. Sorry, let's put that again. So he moves around, he sees something on the coffee table, then he looks at the TV, he swipes his finger to turn it on, and then he uses a pin and push gesture to send a like. Step 2 is creating sketches in Pronto's playback view. The previous video is loaded, and now the designer can use the tablet in the physical space to position objects in the current frame of the video. This happens in real time. The position in the physical space is represented in the current video frame. The tablet works as an avatar to position sketch layers. For example, here, the designer decides to put a new sketch on top of the coffee table and create it. After that, he can change the size. And in this case, he will draw a weather widget showing that it is sunny. The asset remains in place during playback. Step 3, enacting and animating. The designer adjusts the video and moves towards the TV to create a sketch in the screen. Then he draws the content in the TV by creating a new sketch layer, resizing it, and in this case, he will draw a cute cat. Now the cat needs to be hidden and then revealed with a flick gesture. The designers manipulate the top handle and push it down. He can use the enact button on the left to start recording and demonstrating the system response. In this case, he is pulling the same top handle, but going up. He presses the enact button and does the animation. The animation is saved in the timeline and its duration can be adjusted to match perfectly the user input. For the like interaction, he first needs to create a heart at the pinch position. The designer wants the heart to fly towards the TV with a custom spiral animation. Now, instead of manipulating handles, we will move the whole sketch, the heart, with the tablet position as a proxy. This is what we call direct enaction. The designer presses enact and then moves towards the TV with a spiral path. The animation is saved and he can adjust the duration in the timeline. Finally, to make the cat react, he uses the same process with a shake motion. And this is the final result made in less than 4 minutes. We can see the weather widget on top of the coffee table, how the user turns the TV, and then sending a like with the response. In terms of related work, there are many AR prototyping tools, but they require extensive programming. However, there are a few general non-specialized prototyping tools such as Dart. However, it still requires extensive coding skills to customize the experience. Other tools combine AR and Wizard of Oz, but without the video capturing capabilities, making it difficult to synchronize. For example, 360 Proto specializes in 360 experiences by creating paper prototypes. Proto AR combines paper sketches with clay to illustrate quasi 3D effects. In contrast, Pronto focuses on dynamic interactions. And Pintar combines digital sketches on a tablet with live AR tracking, but it does not support creation of custom animations and uses video shots as an output and not as a design medium. In terms of the implementation, we have these two views, the recorder and the playback. The recorder view is a typical AR session, capturing video frames, fixing the word origin, tracking the position of the tablet, and also the position of assets. This information is saved during recording in 2 files, one that has the timestamp transformation and a movie file with the pixel buffers. Then we recreate the 3D scene in the playback view. But without the live video feed, we use the video file as the background of the camera. And that will mimic the 3D scene and is represented in the playback. To evaluate Pronto, we conducted an expert review with 6 AR designers. The first task was to recreate the Pokemon Go capturing interaction with mid-air gestures. All the participants were able to finish this task in less than 20 minutes, and it took 12 minutes in average. Then task 2 was open-ended. For example, P1 created a narrative-based experience. He created an off-screen attention guiding cue, and then this little animation with the V's. P2 created a racing game with some difficulties. So let's move on. P5, for example, did a smart home experience where each bin knows the type of garbage that it can receive. And P4 created a product tutorial with instruction to operate this tumble. Basically, participants successfully recreated these advanced AR mechanics using Pronto in a short amount of time. The average completion time was 30 minutes and 3 seconds. And all participants rank high Pronto's capabilities for exploration and creativity. In terms of future work, we would like to suggest several directions. One is adding collaboration to support multiple designers, to add comments and annotations, and also to take in consideration depth to fix occlusion, and to move from video illustration towards interactive prototypes. Thank you.
Thank you very much, Shaman. Again, imagine the, the applause coming here. Anyone want to ask a question to Shaman here after the presentation? Please type your name in the chat. I could perhaps start by asking if this work is designing for or in VR.
So this work is specifically for augmented reality, and it's for designing in AR. So you can use only one tablet in this case, and at the same moment that you are enacting and rehearsing your design idea, you can create the sketches in place. So we have this capture first and draw later workflow. And designers, we got mixed responses of that. There are more details in the paper, but all of them understood how to do this. First, they need to act out, to think that the system is there, and then they will add the sketches to generate the illustration. But some participants wanted to put the assets right there in AR, and it's something that we are exploring right now, actually.
Thank you very much. I can see there is a James who has a question, but James, could you please turn on your camera? So either unmute your microphone if you want to ask the questions, or write the question. Okay. Maybe that's not a real question.
Yeah.
Yeah. Sorry, this was a lot of cues many times at many places trying to run this. So I can continue here because I also started when I thinking when I saw your presentation regarding if this is actually prototyping or if this is more about sketching a prototype.
That's a good question. Many people use this terminology differently. For example, Bill Buxton talks about sketching and prototyping as two different concepts. There are other authors that consider prototyping in the whole spectrum of design. So basically, this will be considered exploratory prototyping, and I'm taking exploratory prototyping as a synonym of sketching interaction. But yes, definitely this is sketching in the sense of sketching and interaction. It's not trying to answer a question like more an experimental prototype will do. It's trying to explore. So definitely yes, it's sketching.
I'll do my last question then. Since I have prepared, I can just as well ask you. So yes. Have you considered various degrees of fidelity for this? Because it seems like it's mostly hand sketching.
Yes. So we wanted, because in our formative interviews, all of the designers mentioned that creating 3D assets, it was painful. Of course, we could have an option where you have a catalog of assets and you just import the one that you need. And that works great if you find something that you need. But if you want something that is not there, is damaging the speed that you need in early stage prototyping. So we took a complete sketching approach, but we have features that once you have a sketch positioned in a place, so imagine this weather widget on top of the coffee table. If later a designer will do a high fidelity asset, he can just replace the sketch with the new asset, and the position, the animation, everything is preserved. So it's really easy to iterate from this low fidelity to higher fidelity, even more than in, I would say, web design or other type of mobile design.
Okay, thank you very much.
There is a question there.
Yes, from Junie.
From your experimental setting, what could you exactly learn from user reaction? How do people draw in AR environment? That's good. So what we saw many things. In the open-ended task, they were bringing an idea that they had. For example, participant 6 was really obsessed with fire, and he wanted to do a first-person shooter. So he was just starting drawing flames and then positioning the flames on top of the fingers. So that was one of the reactions that we saw, maybe some design fixation from the get-go. I'm not sure if it will be interesting to draw in 2D and then import it in the 3D environment. But it's something that we didn't explore much as how people draw in AR. We explore more how they were using our tool. So I don't have like really clear patterns of how they draw in AR, but they definitely like the idea of having a 2D canvas to draw instead of having actual 3D spatial drawing. There are other papers that explore more that area, but I'm not so sure what are the takeaways of that.
Okay, thank you. I also noted, if I compare your studies, so Clement and Germain, because Germain, you used the users that you tested your system on were highly experienced, but Clement, your system was tested with users with limited experience, and whether this has an impact on the results you get somehow. I don't know who this question is for, maybe both. I'll just continue babbling here, and we have a break, I think, officially, but...
It's weird because we really wanted to have this for people that doesn't have any prior knowledge, and we tried informally with those, and we got mixed results. But we wanted to see if this was valuable for experts in AR design, and for us it was really important because if experts see value in a tool like this, we are pretty sure that the low learning curve can help many stakeholders that they do or do not have AR experience to start using lightweight tools like this as their starting point for doing AR design, because it's challenging so far, I would say.
Yes, okay, thank you very much. We need to wrap up this session because we have some new speakers who will like to test their presentations. So thank you very much, Germain, and sorry for all the technical problems. I hope now we know how to run these sessions. We learned a lot. So thank you all for hanging out here. And yeah, and applause to you again, Germain.